Okay, good morning, ladies and gentlemen. Today's lesson on density will be very similar to some of the concepts we saw in yesterday's lesson. Yesterday we talked about unit conversions, and although we'll see some unit conversions today, today's focus is primarily on the fact and the concepts here that the density of an object is equivalent to the mass of the object divided by its volume. So we'll oftentimes see a weight per cubic unit of volume. Okay, so we'll see grams per cubic centimeter. There's certainly a lot of different ways that density can be expressed. And one thing I will say, and we talked about this a little bit yesterday, is that oftentimes in the end we're looking for the weight of something, and the way we're going to find that weight or its mass is by taking the density component that's given and multiplying by a volume that we can calculate. So we'll go through some examples quickly on the front page here, and what I'm actually more interested in is hopefully getting to the two examples on the back, because those are actually old Regents exam questions of how you can see density modeled in a short answer type situation. So the first question is about mercury metal being poured into a cylinder that holds exactly 22.5 milliliters. And what I'll tell you about this holding that many milliliters, that's really your volume component. I realize we're typically used to seeing maybe that unit given in terms of a cubic unit. So if you want to add that in there, that the volume is that many cubic milliliters, that's probably a unit that was missing from there. But if the mercury used to fill the cylinder weighs this amount, 306.0 grams, calculate the density. So if density is mass over volume, the density of 306.0 will get divided by the volume, which is the 22.5 cubic milliliters. Let's see if the calculator's working here. So if I do 306 divided by 22.5, we wind up getting 13.6. So the volume, based on that volume there, we can get that the density is 13.6. Okay, and then since we had grams on top, it would be grams per cubic milliliter. Okay, so you'll see a lot of density in examples given in terms of those units, right? A mass per volume in cubic units. So in this question, we just have to take those two components, divide them out to get the specific density here. If we go ahead and take a look at number 2, it says, what is the weight of ethyl alcohol that fills a cylinder whose diameter is 10 millimeters and has a height of 100 millimeters? The density is given as 0.789 grams per cubic millimeter. So if we're paying attention to something we talked about yesterday, the dimensions of the cylinder are the same type of cubic units of volume I need as far as the density is concerned. Okay. So it says in the end, what is the weight? Okay, so the weight would be the mass in this formula here. And as a reminder, to get the mass, we're going to take that density and multiply by the volume. The volume is not given to us right away. We have to find it based on the fact that it is a cylinder, and it's a cylinder whose diameter is 10 and has a height of 100. So if I do the volume of a cylinder will be pi r squared, and the diameter is 10, which means the radius is 5, and the height is 100. So altogether, we get a volume here of 2,500 pi. Okay, and this would be cubic millimeters. And again, making sure we pay attention to those units each time, since the density is given in terms of cubic millimeters. We can multiply that density component of 0.789 grams per cubic millimeter by the volume that we just calculated, and in the end we should find that the weight is approximately to the nearest tenth 6,198. Oops, hold on. 6,196.8 grams. So again, that weight calculation that we're doing in this case, that's something that we will pretty typically be asked to do. I'm going to pause here for a second, but go ahead and take 2 minutes and try number 3. We'll get to number 4 in a moment, but actually have somebody come up and pause the video quick, and then go ahead and try number 3. Okay, so as far as number 3 is concerned, it says a wooden cube has an edge length of 6 centimeters and a mass of 137.8 grams. determine the density of the cube to the nearest thousand. Okay, so if density is mass over volume, we know that the mass is 137.8 grams. And the cube has an edge length of 6. So based on the edge length of 6, the volume of the cube would be 6 cubed, which would be 216. So you can either type in 6 cubed on the calculator as is, okay, or you can type in 216 if you know its value there. So the density that I'm getting is 0.638. Okay, and this would be grams per cubic centimeter. And if you look at this table over here that's given up to the side, this is actually a sample regions question as well. The densities are all given in grams per cubic centimeter. And we don't necessarily know that we have to use the table yet until the next part, which says state which type of wood the cube is made of using the density table. So we have a lot of different types of wood that are given. Clearly we're looking for the one that has a density of 0.638 grams per cubic centimeter. And that corresponds specifically with the ash wood. Okay. So I think based on the values that were given there, hopefully that wasn't too challenging for us to plug in the volume as 6 cubed and calculate the density from there. The last thing we're going to talk about on this first page here is in number 4. It's a little bit of a different type of density calculation. We're talking about bacteria growing in Petri dishes. And we have Petri dish A and Petri dish B, each with a certain number of bacteria. So there's 40,000 in Petri dish A, there's 72,000 in Petri dish B, and we're given the diameters of each of those dishes. We want to find out which Petri dish has the greater population density. And I've seen population density asked on the Regents exam before. So again, population density is a little bit different than our traditional density calculations that if it's population, what we're going to do is we're going to take the population and divide by the area over which that population is spread out. Okay, so I think that even though we're relating this to bacteria, certainly you can relate this to different cities, you know, across the state or the country even, as far as even though one city might have a greater population than another, it doesn't mean that the density of the population is necessarily more when compared to another city of a lesser population. So in this specific case of population density, if I start with Petri dish A and I calculate its population density, I would take the population of 40,000 and divide by the number of square millimeters in this case that the bacteria in that Petri dish are occupying. So the area of that circular region would be pi r squared. So pi times the radius. If the diameter is 51 millimeters, the radius is 25.5. Okay. So to take the population, divide by that area, pi times the radius squared. And if you type that into your calculator, so the nearest hundredth, you should get approximately, and again, just be careful with that denominator. You really want to keep this whole thing in the parentheses, otherwise you're using what I like to call a fancy fraction. You should get that this is 19.58. Not square millimeters. It's really that many bacteria per millimeter squared. Okay, so the way we express the density in this case is it's the number of bacteria per square millimeter that they're existing in this Petri dish. So on the other hand, we have this Petri dish B here, and certainly has a greater population, but based on the size of the Petri dish, we'll see if this population density is larger or smaller than that of Petri dish A. So for B, we have 72,000 for the population. Divide by the area of that Petri dish. Pi r squared here would be, the radius is 37.5 squared. And just to double check that my calculator is still working here, if I do 72,000 divided by, I'm just going to put this in parentheses here, pi times 37.5 squared. All right, I didn't use a fancy fraction, but this is the number you should come up with, whether you use one or not. I got 16.297, so about 16.30 here. So 16.30 bacteria per square millimeter. So even though there are more bacteria residing in Petri dish B. The actual greater population density comes from bacteria dish A. Okay, so the conclusion here, it says, determine and state which Petri dish has the greater population density. So clearly in this case, based on those calculations, we get dish A as a result. And this is also a former Regents exam question, so just to give you a little bit of a different look as to where density might come into play. Okay, so if we go ahead to the back page, then we have two really good examples. I'll tell you 5 is a former 4-point question on a Regents exam, and 6 is actually a 6-point question. We'll actually talk about the fact that there are no more 6-point density applications anymore, but it's a good question regardless. So 5, there's a lot of information going on here. It says a snow cone consists of a paper cone completely filled with shaved ice. Sounds delicious to me. Topped with a hemisphere of shaved ice as shown in the diagram below. The inside diameter of both the cone and the hemisphere is 8.3 centimeters. The height of the cone is 10.2 centimeters. So then we get on to, based on all that information, the desired density of shaved ice is 0.697 grams per cubic centimeter, and the cost per kilogram is $3.83. So we know we're going to do some sort of unit conversion because the density is in grams, and then we have kilograms given for the cost. Determine and state the cost of the ice needed to make 50 snow cones. So there's definitely a lot of information going on here. Certainly to get the cost of the cones, we have to figure out the weight of the cone. And the easiest way to get the weight certainly is going to be by using this density component. And we know that the density is equal to the mass divided by the volume. So we're going to find the mass of the snow cone, but I think that the way that we're going to calculate this is, first of all, the dimensions up here are at least given in centimeters. So if I calculate a volume, we'll be in the correct unit for the density component. And then we'll convert that to a weight, but that weight will be in grams. So I'll have to think about what do I do with that information to get to kilograms. Okay, let's start with some volume though. So we got a hemisphere on top of a cone, right? So based on that, let's start with the hemisphere's volume. The hemisphere, we did this yesterday quickly. We know it's 2/3 pi r cubed. So the radius in this example is going to be half the 8.3 as the diameter. So it's going to be 4.15 cubed. And before I even type that in, let's actually add to that the volume of the cone below it. So volume of a cone member is 1/3 the base area times the height. So 1/3 area of the base is that circle, pi r squared. So the radius of that cone is the same as the radius of the hemisphere. This time I'm squaring it times the height, which is given to us as 10.2. Take a second to type that into your calculator. See what you get as your volume in cubic centimeters. So we're going to get a volume out of this that will be in cubic centimeters. There should be a lot click-clacking of calculator keys right now. You're typing, giving you another 5 seconds. Hopefully that was enough time. If not, you'll double check me later. The volume that I came up with in cubic centimeters is 333.654. Okay, and that's not my final answer yet, so I'm going to put ... after that. Okay, but that's the number of cubic centimeters we have for the volume. Okay. Now that I have that information, I can calculate the weight in grams of a snow cone based on that density component. So if I take this volume, and remember that the mass is equal to the density times the volume. We know the volume, we know the density, so take that and multiply it by 0.697. That's going to tell you the weight in grams in this example. So if I do that multiplication, we get 232.55, and again, it's not my final answer yet, so it's that many grams is what we get from multiplying that by the density. Okay. So now, in the end, if I want to find out the cost to make 50 snow cones, there's a couple different ways you can go from here. What I'm going to do is I'm going to convert this automatically into a weight in kilograms. This way I'm going to use the correct conversions to get my cost in the end. So to convert this to kilograms, to go from grams to kilograms, remember that there are 1,000 grams for every kilogram. So I have to take this and I divide by 1,000 to now come up with the number 0.23255 kilograms. Okay. And now that I have the weight in kilograms, we have two more calculations to do. The final steps is it's $3.83 per kilogram. So multiply this by $3.83. But don't forget, we're also wanting to make 50 snow cones. So there's a lot of little details to pay attention to in this problem. So then I have to take that cost per snow cone and multiply it by 50. And in the end, if I multiply all this together, the cost to make 50 snow cones is $44.53. And knowing that information, I would say, is pretty important to us, because if I want to make a profit from selling such snow cones, we'd certainly want to know how much it costs to make them. So if you look at all the math that we followed through here, certainly as we go through the process together, it sometimes is easier than attempting this on your own. But again, with more practice with examples that are similar to this, I think we'll start to feel more and more confident with the process. Okay. Last thing we're going to do is go ahead and take a look at the question at the bottom. And again, even though this is a 6-point question, I like this question as far as a volume and density application are concerned. So if you have this in the picture, a water tower that's modeled by the two-dimensional figure beside it. So we have a 2D representation right here of this three-dimensional water tower. And actually, if you drive on Route 31 in Fairport, the Fairport water tower is very similar in shape to this one that you're looking at right here. You know, next time you drive by it, you'll never think of this water tower in the same way again, because it can be modeled by a hemisphere at the very bottom, right? So if you take a look at that half circle in the three-dimensional space is the hemisphere. And then from there, we get in the middle a cylinder. Okay. So you can see how if you rotate this rectangle about the dotted line, you're going to get the cylinder. And at the top, we have something that is cone-shaped. All right, so we have these three-dimensional objects that are kind of put all together to make, in total, a water tower. So you're given some other information. Let C be the center of the hemisphere, and then D be the center at the base of the cone. If AC equals 8.5 feet, that's labeled. BF is 25. And the measure of angle EFD is 47. Determine and state to the nearest cubic foot the volume of the water tower. Okay, so to find the volume of the water tower, we're going to have to find the volume of a hemisphere. That's the bottom. Plus the volume of a cylinder in the middle, plus the volume of the cone that's on top. Okay. So if we start with the hemisphere at the very bottom, we know the radius of the hemisphere is 8.5, so that makes our job a little bit easier to say that 2/3 pi r cubed is the formula, so 2/3 pi times 8.5 cubed. Okay. Volume of the hemisphere. To calculate the volume of the cylinder. The volume of the cylinder in the middle has the same radius, right? This radius would be the same as the radius going this way in the hemisphere. So we know what pi r squared h is the formula, so it's going to be pi times the radius of 8.5 squared times the height, which is given to us as 25. Okay, and one more piece to go. We got that cone on top. The cone's volume, very similar to that of the cylinder, but remember it's 1/3 pi r squared h. The radius is still the same. We got that radius of 8.5 squared. So the only difference is that between a hemisphere and a cone is that this height right here, from E down to point D, does not necessarily have to be 8.5. And in fact, I'll tell you it's not 8.5. It's pretty close to that. But in order to find the length of the height, there has to be some reason why they gave us that this angle is 47 degrees. Now remember that this side from F to D right here is a radius, so that this length is 8.5 as well. So given that angle of 47 degrees, I'm looking for the height. Given that the adjacent side is 8.5, maybe some of you are shouting out and jumping in your seats right now saying, SOHCAHTOA, TOA, trigonometry. Because what we're dealing with here is that the height is the opposite side of the 47 and 8.5 is the adjacent. So out of SOHCAHTOA, TOA is what we want. We want some tangent here. I'm actually going to do the work right up here. That to get the height, you would do tan of 47 degrees equals opposite over adjacent, so that equals the height over 8.5. Certainly a little bit complicated to get that height value for the cone, but once I have that, I'll just substitute it in. And actually, I'm going to leave it in an exact form. So what I mean by that is I'm not going to go to the calculator yet. The height would equal 8.5 times tan 47. Right? If you multiply both sides by 8.5 there, that's what we get for the height. So if I come on down to where the height should get plugged in for that cone, I'm going to take this whole thing and plug it in right here. 8.5 tan 47. Now remember, since we're doing a little bit of trigonometry here, your calculator should be in degree mode. So I'm going to actually make sure I change that on my calculator. My calculator currently says radian. So if I switch it over to degree, quit out of there. All right, let's see if I remember all these numbers, by the way. So it's going to be 2/3 pi r cubed. So 2/3 pi times the radius, which was 8.5 cubed. So there's my hemisphere, plus the volume of the cylinder, which was pi times radius squared, 8.5 squared, times the height of 25. Finally, plus the cone, which was 1/3 pi, the radius squared, so 8.5 squared. And then at the end, to avoid any sort of rounding issues at all, I'm going to go ahead and type in that whole height, 8.5 tan 47, close parentheses twice. I'm in degree mode, so that looks good. And hopefully I did this correctly. The volume that I got is 7,650. And it says to the nearest cubic foot. So we're good to go. 7,650. And all said and done, cubic feet is how much water this tower can hold. Okay. And finally it says at the very bottom, so by the way, that would have been +4 up here. That's probably where you would have to stop on today's Regents exam, but this was worth another 2 points down here. The water tower is constructed to hold a max of 400,000 pounds of water, and if water weighs 62.4 pounds per cubic foot, can the water tower be filled to 85% of its volume and not exceed the weight limit? Okay. So what we're going to go ahead and do is take the volume that we have, 7,650, and we're going to multiply that by the density that's given to us, which is the 62.4 pounds for each cubic foot. So that's going to be the weight of water if the entire water tower was filled. But one last component is if we only want it to be filled 85%, multiply that by 0.85. Okay. So you can do this all at once, you can do it in separate steps, but this would be the entire weight of the water tower filled to 85% of its max capacity. We wind up getting 405,756 pounds of water is what the weight would be when it's filled to 85%. Okay, since we want to only hold a max of 400,000, can we hold up to 85% filled with water? The answer is no. Unless we want a big spillage out in the streets of Fairport. So anyway, that's all I have for today, guys. Tonight's homework will be passed out in just a moment here. Go ahead and work on that. And as a reminder, please make sure you come in with specific questions on last night's homework and tonight's homework when we come back to class tomorrow. Thanks, guys. Have a good day.